All right, hello class. So welcome to this Unit 8 review. So I wanted to go over some of these questions in case you wanted to, you were struggling with some of the content and you wanted to, kind of see how it was done. So in the test, there's going to be, conceptual questions, true and false questions, as well as, word problems that involve studies where you have to do a hypothesis test, kind of like in the practice where you have to, go through each of the steps. They'll ask you a specific question for a specific step. What is the hypothesis? Where does the claim belong to? What is the test value? That kind of stuff. All right, and you'll have four different types of problems. You'll have one for each type of test. So you're going to have to determine: do I use a z-test? Do I use a chi-square test? Do I use a t-test, etc. So you'll have at least four of those, at least one of each type of hypothesis test on the exam. All right. So let's go over some of the conceptual stuff. Some of the conceptual stuff, this is like only some of what I could ask. So make sure you go back and you go through the vocab, and then that you understand how the hypothesis test works. Okay. So for the first problem, we're asking, so it says no error is committed when the null hypothesis is rejected when it is false. Okay, so the concept here is you have to know whether it's a type 1 error, whether it's a type 2 error, or whether there's no error being committed. Okay, so remember real quick that there's a type 1 error and type 2 error. And remember that a type 1 error happens when you reject the null hypothesis incorrectly, right? So that means that you're not supposed to reject it because the H0 is actually true. Okay, it's actually true, but you rejected it, and so that's an error. And for a type 2 error, you failed to reject H0 incorrectly. So basically, you don't reject it when it's actually false because you were supposed to reject it. Okay. Now, in this example, and remember that the type 1 error is given by alpha, which is your level of significance, and your type 2 error is given by beta. All right, so I quickly mentioned that in, I believe it was 5.1 or 8.1. But just to kind of remind you, the type 1 error is given by alpha, which is what you have to choose in step 2 of your test. And then your type 2 error, we didn't really talk too much about it, but it's given by beta. All right. So it says here, no, if the hypothesis is rejected, but it is false, then in that case, there is no error being committed, right? Because you're supposed to reject it because it's false. So this is actually true because there's no error being committed there. When you're conducting the t-test, the population must be approximately normally distributed. So again, you have to know like what conditions must take place for you to choose a certain type of test. Okay, so this question could be asked for the t-test. It could be asked for the chi-square test. I could ask you a question on if I can use the z-test for proportion, for example. So in this case, we're talking about the t-test. If the population is approximately normal, that means that yes, we can actually use a t-test. The population must be approximately normal for you to use a t-test. Remember that in addition for it being normal, you have to not know the population standard deviation, so that must be unknown. And you also have to have a small sample size, okay? But in addition to that, the population must be normal. Now the test value that separates the critical region, or so it says the test value, this should say separates, there shouldn't be a dot there. The test value separates the critical region from the non-critical region. This is also known as the test statistic. So remember, this is the test statistic z-test or t-test. And remember, the critical region is known as the rejection region. So this is also known as rejection region, and this is the non-rejection region. So remember that when you're given a curve, it doesn't matter if it's chi-square or not, there's usually a rejection region, right? So this will be like the rejection region. And this will be the non-rejection region, also known as the non-critical region, where you fail to reject H0. So remember the value that separates those two is actually the critical value, not the test statistic. So like in this case, Z crit or T crit or chi-square crit, that's the critical value that separates those, not the test value. So this is actually false. Okay, the values of a chi-square test cannot be negative. So they're saying that the chi-squared value cannot be negative. And that is actually true. Remember that the chi-squared curve is actually positively skewed. It's actually skewed to the right. And it looks like that. And remember that this value here is when the chi-square is 0. And then here it goes up all the way up to infinity. So it basically just goes bigger and bigger. So these right here represent the positive chi-squared values. Okay, so those values are actually positive. There are no negative values. Whereas if you look at a Z or a T distribution, it usually starts with 0 in the middle, and then these values are negative values, right? And then these values are positive values. Okay, so that's the difference between the T and the Z, as well as the chi, compared to the chi-square. So the chi-square is never going to be negative. So that is true. The chi-square test for variances is always one-tailed. That is actually false, because if you look at the chi-square distribution, even though it doesn't look like it has two tails, it really does. And you can actually do a two-tail test with a chi-square. You just do it like this. So like if you have a two-tail test, then you would just use those two sides of the chi-square distribution. So yes, you could do a two-tailed test with a chi-square distribution. So it is possible. So that would be false. All right, so we're going to go ahead and look at the hypothesis testing problem. So the first thing we want to do is determine which hypothesis test to use. Do we use a z-test, t-test, z-test for proportion, or chi-square? Next, we want to perform the hypothesis test. If we are performing a z-test, then we have to use the p-value and critical value methods. Otherwise, just use the critical value method. Okay. The reason I say this is because for the z-test, I showed you how to do both the p-value and the rejection value, or rejection critical value method. But with the other ones, I only showed you how to do the critical value method. Okay, so let's look at number 6. So it says, a real estate agent believes that the average closing cost of purchasing a new home is $6,500 over the purchase price with a standard deviation of $120. So clearly that's the claim, and it says that the average cost of purchasing a new home is $6,500. So that's your mu, and it's saying that it's equal to, because it says the word is, over the purchase price with a standard deviation of $120. So that statement right there, that standard deviation, that's your sigma. Okay, because that's part of your population statement, your claim. In this case, it's not like your claim, but it's saying that that's for the population. Now, she selects 40 new homes, so that's your n sample size at random, and finds that the average closing costs are over $6,600. Okay, so this should say $6,600 over $6,600 over the closing cost, over the purchase price rather. Sorry, that's just a typo. So our $6,600. So this average cost right here is from the sample. So this right here is your X bar. Okay. Now this is clearly your alpha, 5% significance level. So we're going to go ahead and label those variables and determine the claim and all that. Okay. So for number 6, we have that the claim is that the average closing cost is equal to $6,500 over the purchase price. Okay, so it's just $6,500. That claim belongs to the null hypothesis because, remember, null hypothesis is a statement of equality. And our HA or H1 is going to be not equal to. The reason it's not equal to is because the problem does not tell us whether the researcher thinks it's greater than or less than. Okay, It's only saying what the claim is, right? So therefore we use not equal to if it doesn't tell us. So first off, because the sample size is 40 and it's greater than 30, so because the sample size is greater than or equal to 30, this means that we use a z-test for a mean. And we're dealing with means here, right? Because we're dealing with mu. So first off, I didn't even write that down. So first off, we're going to use a z-test for a mean. Because in this case, the sample size is greater than or equal to 30. All right, so that's what we're going to use. So let's label our variables. So our n is equal to 40 homes. Our x bar was, I believe it was $6,600. I got to go ahead and double check. Our sigma, I believe, is 120. And our mu is from our claim, which is $6,500. So let me double check those numbers. So sigma is 120, yep, n is 40, and x bar 6600, and then alpha is 0.05. Okay, and then alpha is 0.05, 5% significance level. Okay, so now we're ready. We did our hypothesis statements. Now, based off of this, based off of the HA or H1, it's a two-tailed test. All right, so we're going to have to draw that curve eventually. We'll do that in a little bit. Now, so let's go ahead and do the p-value method. Or let's calculate the test statistic first. So let's calculate the test statistic, which we're going to call z-test. I'm just going to call it z-test. Remember that the formula for the test statistic is x bar minus mu divided by sigma over square root of n. That's the formula from your notes, 8.2, I believe. We're just going to plug in our numbers. So we have 6,600 minus 6,500 over 120 over square root of 40. And again, you can use a scientific calculator. You can use your phone to do this calculation, or you can use what I would suggest is using Desmo scientific calculator because it's really useful. Either way, the answer, so the z-test is going to be 5.27. So that's the test statistic, rounded to 2 decimal places. All right, next we're going to do the p-value method. And so we're going to show you what the difference is between the p-value method and the critical value method, okay? So with the p-value method, we have to actually calculate the p-value based off of the z-test, okay? So we know that we're going to draw our curve. And, usually it starts at 0, goes by ones. So our z-test is 5.27. So that's all the way, in fact, that extends all the way over here, right? Now, because it's a two-tailed test, I have to do it on the other side. So I'm going to go ahead and do a negative 5.27 here, okay? This doesn't mean that I have 2 test statistics. It's just saying that I have 1 test statistic, but I have 1 positive and 1 negative version. That's because that's how you calculate the p-value, is by, if you have a two-tailed test, you need to put both sides, okay? But I only have 1 test statistic, so just be careful with that. So I'm going to shade the p-value in blue. I normally shade p-value in blue and rejection value in red. Okay, we're not doing the rejection regions here. We're doing the p-value method. So what we got to do is look up, remember, we got to look up the area on the z-chart, right? So we need to look up on the z-chart to find the p-value. Now we have two regions. So if I know what this blue region is on the left, that means I know what the blue region is on the right. So let's look this up. Remember, the z-chart gives you the area to the left. So if I look up the area to the left, that's going to give me this blue region here. Okay, so let's go ahead and look up the value from the z-chart, negative 5.27. All right, notice that the smallest z value that I have is negative 3.49. I don't have anything past that point. Okay, so since that value is too big, I'm going to go to the bottom where it says here, you see this statement right here. For z values beyond negative 3.49, use this as your area. So we're going to use 0.001 as our area to the left right here, okay? We're going to use 0.001 for that area to the left. All right, so let's go ahead and use that area. Let's go. So this is going to be 0.0001. That's my area. That means that this is also going to be 0.0001 because they're both the same area. So that means the p-value is when you combine those two together, which basically double it. So that's going to be 0.0002. That's my p-value to 4 decimal places. All right, so now remember, for the p-value method, you have to compare p-value to alpha. If this is true, if it's less than or equal to alpha, you're going to reject the null hypothesis. So what's our p-value? Well, we already calculated it. Our alpha was 5% significance, 0.05. Now this is actually true. P-value is less than or equal to alpha, which means our decision here is to reject the null hypothesis. Okay, so we know we're going to reject. So now let's show you the critical value method. For the critical value method, you have to find your critical values. Okay, so we're going to have to find them, ZC. Since it's a two-tailed test, that means we have 2 critical values. So what are the alphas that I'm going to be using here? Or what are my areas? Okay, so my areas that I'm going to look up. First, I got to take my alpha and divide it by 2. So I'm going to take my alpha and then divide it by 2. Okay, so that's what I'm going to do for I'm just going to say alpha divided by 2, which is going to be 0.05 divided by 2, which is 0.0250. Okay, that's my area. So that means I'm going to look up this area, and then I'm also going to get a z-score for that. Now, because it's two-tailed, I know I'm going to have a plus or minus version of that. So I'm going to get to so this is my area that I'm going to look up. I'm going to look up an area that is as close to this as possible. So let's go to the z-chart again. Look up an area that is as close to that as possible. In this case, the closest area is that one, which is exactly the same area. So what's my z-score? Well, it's going to be negative 1.96, because 6 is all the way up there. Okay, so my z-score is negative 1.96. Now, because it's a two-tailed test, that means I have both positive and negative 1.96. So I'm just going to go ahead and do that. I have 2 of them. All right. So now I'm going to draw my normal distribution. And I'm going to draw my 2, I'm going to label my 2 criticals. This time I actually do have 2 criticals, like 2 values that are considered criticals. Whereas here I only had 1 test statistic. Here I have 2 criticals, right? Because of for a two-tailed test. So I'm going to label this in red for rejection. These are known as my rejection regions, okay? So that means if I'm in that red region, I'm going to reject the null hypothesis if I'm there. So the area for each of these is 0.0250. That's my alpha divided by 2 that I got earlier. Okay, so that's the areas for those. Not that you need to know that for this. So now the next step is to calculate the z-test, but we already did that. We did that right here. So label that on your curve. So z-test is 5.27. That's right over here. So in that case, it looks like we're inside our rejection region. So because we're inside our rejection region, we're going to reject the null hypothesis. Okay, so that is the difference between the critical value method and the rejection and the p-value method. Okay, so critical value method, you see if it's in the rejection region. The p-value, you just got to calculate the p-value and then compare it to alpha. So that's the difference between those two methods. So now, whichever method you decide to use, you still got to draw your conclusion, right? So let's go ahead and write our conclusion. I'm only going to show you how to write this once, like fully, and then the other problems I'm not going to write the full conclusion because that's going to take some time. All right, so first off, since we rejected, that means we have enough evidence. So we're going to say there is enough evidence Okay, so keyword is there is enough evidence. Otherwise, if you fail to reject, there is not enough evidence. So there is enough evidence at the, in this case, we're talking about the 5% level of significance, to the next key term. Since the claim belongs to the null hypothesis, we're going to use the word reject. Otherwise, you would use the word support. Reject the claim that, and then you're going to write your claim. Insert your claim. What was the claim? The claim was that the average closing costs are $6,500 over the purchase price. All right, and then so that's your claim. Okay, so those are the three things that you're going to do. From here on out, I'm only going to tell you what the key phrases are. I'm only going to tell you whether you're going to use enough or not enough, or reject or support. I'm not going to write out the entire conclusion. Okay, but you should be doing that when you show your work, writing out the entire conclusion. All right. All right, so now we're looking at number 7. So a copy editor thinks the standard deviation for the number of pages in a romance novel is greater than 6. A random sample of 25 novels has a standard deviation of 9 pages. Use a 5% significance level. All right, so here we're talking about a claim belonging to the standard deviation. So it says the editor thinks, so that's our claim, that the standard deviation, so that means he thinks that the standard deviation, which we call sigma, lowercase sigma, for the number of pages is greater than 6. All right, so that's our claim right there. So, since we're talking about sigma, this means that we're using a chi-square test. Okay, so for part A, we're looking at a chi-square test. That's the symbol for the Greek letter chi. Remember chi-square? I'm just going to write it in English though, and like using Roman numerals or Roman letters. So a chi-square test. So our claim, remember that when we do our claim, it's going to be sigma. You said sigma was 6, right? The standard deviation of the pages in a novel. But remember, the claim has to be written in terms of the variance, not the standard deviation. Remember that the variance is simply the square of the standard deviation. So the variance is going to be, you're just going to square it. So we know that 6 squared is 6 times 6, which is 36. Okay, and that's my full claim. So now we're going to do our null and our alternative hypothesis. We'll call this HA. It doesn't really matter. You can say HA or H1. So this claim is a statement of equality, so we're going to assign it to the null hypothesis. So this is our claim. All right, so now in this problem, it doesn't say what the researcher thinks. If the researcher thinks, actually it doesn't really matter because it says it's greater than 6, and I wrote equal to. So this should be greater than. I apologize for that. It says that the person claims that it's greater than. So this should be greater than. Now, so this means that this is incorrect. I apologize. So the claim is that it's greater than. Now, this is a statement of inequality because of that greater than symbol. Therefore, that belongs to the alternative. Okay, so see what much of a difference it makes. If you put an equal sign there for the claim, that belongs to the HO, but like I mistakenly did. But if you read that it says greater than, the claim becomes greater than and automatically gets assigned to HA because it's strictly greater than. And now the HO has to be the opposite of that. So the HO is going to be less than or equal to. Don't forget that equal to symbol. Don't just say less than. It has to be less than or equal to 36. The HO has to have some kind of equality in it. All right. So that's my HO and HA. So now let's go ahead and label the rest of the stuff. So it says a random sample of 25 novels. That's my N. Standard deviation of 9 pages. That's my sample standard deviation. That's S. That's for my sample, right? So S is equal to 9. All right, my alpha is 5% here. So let's go ahead and label everything that we know. So we know that N is 25 novels. We know that S is 9, which means that S squared is 9 squared, and 9 squared is 81. All right, and then we know that our alpha is 0.0500, 5%. Okay, so we know those things. Let's go to the next step. We're going to actually determine what type of test, what direction of the test that we're dealing with. So looking at this HA, it's going to be a right-tailed test. All right, so now we know it's a right-tailed test. We need to calculate our degree of freedom as well. So let's do that. Because remember, for when you're doing a chi-square test, you need to calculate your degree of freedom, which remember is n minus 1. So in this case, we have 25 minus 1, which is 24. So that's my DF is 24. So we're dealing with a one-tailed test, right-tailed, 0.05 as my alpha, and 24 as my degree of freedom. So we're going to look this value up to get the critical value for chi-squared. So we're going to do this to get the critical chi-squared. Remember that the chi-squared, I'll go ahead and draw the curve because we need to actually draw it. Remember that the chi-square curve is skewed to the right, is positively skewed. So, and it's a right-tailed test, so we know that we're going to have to find our chi-squared critical here, whatever it is, and we're going to shade to the right for the right-tailed test. Okay, so we need to figure out what this chi-squared is. Remember that the chi-square table gives you areas to the right. So if we want areas to the right, then we simply look up the value on the table. If we want the area to the left, we need to do 1 minus. Okay, so chi-square is opposite of the other ones. So let's go to the chi-square table. DF is 24, alpha is 0.05, and we're looking at a one-tailed test. Okay, so let's go to the chi-square table. Okay, so this is a chi-square table. So you notice that if you look at the graph, it gives you the area to the right. Okay, not the area to the left, it's opposite. So that means we are looking for the area to the right, so we're just going to look it up. So what did we say the area to the right was? We said it was 0.05. I actually didn't write it down, but I should be writing that down. So let me write that down for you guys. The area here is my alpha. So this is 0.05. That's my alpha. Okay, so that's the area to the right. So we're going to, on the chi-square table, we're going to look up 0.95. We're going to look up 24 degrees of freedom right here, and then figure out where those two intersect, which in this case, those two intersect right here. So my chi-square critical is 13.848. So 13.848 is my chi-square critical. Okay, so let's go ahead and label that. Okay, so that's my critical value. Next, we got to calculate our test statistic, or our chi-square test. So we're gonna go ahead and calculate that now. So chi-square test. Remember that the formula for chi-square test is n minus 1 times s squared divided by sigma squared. So let's go ahead and calculate that. So n is 25, so we got 25 minus 1. And then s squared, we said it was 81. And then sigma squared, we said was 36 from the claim. All right, so we're going to go ahead and calculate these chi-square tests. So I get a value of exactly 84, or 54 for my chi-square test. So if I asked you to round this to 2 decimal places, you would just use 54.00, okay, for example. So that's my chi-squared critical. So let's label that on our curve. That's going to be definitely onto the right because it's greater than 13.848. So our chi-squared test is 54. All right, so we clearly we are in our rejection region here. So therefore, we reject the null hypothesis. Okay, so we're going to say reject the null hypothesis. So again, I'm not going to write down the entire conclusion. Remember, I told you I was just going to tell you the keywords. For the conclusion, you're going to use the word, well, since we're rejecting, we're going to say not enough evidence, right? So not enough evidence. And then for the other key term, so there is not enough evidence at the 5% level of significance. 2, now since our claim belonged to our, let's go ahead and check. Our claim actually belongs to our alternative this time. So since our claim belongs to our alternative, we're going to use the word support instead of reject. So there is not enough evidence to reject or to support the claim that ... Okay, I'm not going to write it out. And that's problem number 7. All right, so let's look at the next question, number 8. So a recent study in a small city stated that the average age of robbery victims was 63.5 years. So we're talking about average, and that's our claim. So average, kind of mu, was, so basically equal to 63.5. A researcher believes that the result is too high. So now they're actually telling you that they think it's too high, which means that they really think that it should be less than that, right? So instead of it being greater than, they think it should be less than. A random sample of 20 recent victims had a mean of 63.7 years and a standard deviation of 1.9 years. So a random sample of 20 victims, that's n, had a mean, so that's my x bar, of 63.7, and a standard deviation, that's my s, of 1.9. Use a 1% significance level, so that's my alpha. Okay, so first off, what kind of test are we going to use here? Well, because the n is less than 30, and the sigma is unknown, and we assume, it doesn't say in the problem, but we assume that the distribution is normal. Okay, so usually the problem will tell you assume it's normal, but if not, just assume that it's normal. We don't know sigma. We actually only know s, and it's less than 30, so we're going to use a t-test. So t-test for a mean. Okay, so now we know what test we're going to use. Let's label our claim and all that stuff. So our claim is that the average was 63.5. Clearly, that belongs to the H0 because it's a statement of equality. For the alternative hypothesis, HA or H1, the researcher thinks that this result is too high, which means that the researcher thinks it should be less than. And that's my alternative. Remember that if they tell you what the researcher thinks, then you're going to use that as your alternative. Otherwise, you would use not equal to. All right, let's label our variables. So we know clearly our mu is 63.5 from the claim. We know that the x bar from the problem is 63.7. Our n is 20. And we need to know our standard deviation. Standard deviation is 1.9 years, and an alpha is 0.01. All right. So next, looking at the H1, we can clearly see that it's a left-tailed test. All right, so it's going to be a left-tailed test, and we're going to be using the t distribution. We need to figure out, since we're using the t-test, we need to figure out our df. Remember that the df is calculated by doing n minus 1, just like it was for chi-square. So it's 20 minus 1, which is 19. All right, so we have a t distribution. Remember, the t distribution is actually flatter than the z distribution. So I'm going to draw it so that it looks flatter. Okay, so that's the t distribution, and it looks flatter than the z. All right, so what we're going to need to do is we're going to need to figure out what the t critical is. And since it's a left-tailed test, that means our t critical is going to be negative. Okay, so we got to be careful with that. So first step is to find our t critical. So we're going to need our t-table. Our degree of freedom is 19. We're looking at a one-tailed test, and our alpha is 0.01. So let's go to the t-chart. So this is the t-chart. We're looking at the area in one tail with an alpha of 0.01. And we're also looking at, I believe it was 19 degrees of freedom. I'm going to go ahead and double check that though. 19 degrees of freedom. So based off of that result, our t critical looks like 2.539. So because it's a left-tailed test, our critical value should be negative, okay, for a left-tailed test. So it's going to be negative 2.539. Okay, so for our graph here, we have a t-score of negative 2.539. We're going to label that right here, somewhere around here. Now we're going to shade the area to the left for the left-tailed test. All right, and that's my rejection region. Next, we got to calculate our t-test. Remember that our t-test, or our test statistic, is calculated very similarly to the z. X bar minus mu divided by s over square root of n. Instead of using sigma, we use s here, because we don't know what sigma is. Okay, so our x bar from the problem is 63.7 minus our mu of 63.5 divided by s is 1.9 divided by square root of n is 20. All right, so we're going to do that on the calculator, see what we get. We'll round it to actually 2 decimal places here. So we get a test statistic of about 0.47. So we're going to label that on our t curve, t distribution, which is about here. It's not going to be negative, it's going to be positive. Okay, let me erase that real quick. it should actually be over here, not on the left side. So 0.47. Okay, so that's my t-test is on the right side of 0. So this is clearly not in my rejection region. And therefore, I'm going to say that I'm going to fail to reject here because it's not in our rejection. So we fail to reject the H0. So then for our conclusion, this means we do not have enough evidence. There is not enough evidence, okay? So not enough evidence. And my claim belongs to my null, so we're going to use the word reject. So there's not enough evidence to reject the claim that ... All right? Those are my two keywords. All right, and that's problem number 8. All right, so we're looking at problem number 9 now. So scientists think that the standard deviation of radish seeds is 8 days. The standard deviation of a random sample of 60 radish plants germination times was 6 days. Test this claim at a 1% significance level. All right, so clearly the claim has to do with the standard deviation. So that's going to be sigma. The standard deviation of radish seeds is 8 days. So we're going to say equal to. So that's our claim, but remember that when we're dealing with sigma, we use sigma squared, not sigma, right? So for our claim, even though they say that the sigma is 8, equal to 8, really we should say the sigma squared is equal to 8 squared, which is 64, okay? All right, so now you could say technically sigma is equal to 8, but the way that I showed you in the lesson, I do it in terms of variances and standard deviations, okay? But so just keep it consistent with, what the lesson says. All right, so we got H0 and then H1. So in this case, this is a statement of equality. So it's going to belong to the null. And okay, so let's look at the problem. Now the researcher, this is just a claim from a scientist, right? So if you wanted to test this, it doesn't say whether you think it's greater than or less than that. So therefore, we're going to say that the alternative is going to be not equal to. Okay, since there's no other information provided. Okay, so now it says the standard deviation of a random sample of 60 radish plants, that's my n is 60. The standard deviation for the sample was 6 days. So that's my s. And my alpha is 0.01. Okay, so we have n is equal to 60. We have the s was 6 days, which means that the s squared has to be 36. And the alpha is 0.0100, my 1%. Okay, so that's all that they gave us. So now clearly, since we're doing since my claim involves standard deviation or variance, this means that this is a chi-square test. Okay, so this is part B. Part A is what type of test? So this is a chi-square test. Remember, the thing that allows you to perform a chi-square test is if the observations are all independent from each other, and the population is approximately normal, which in this case, so observations are independent, and then approximately normal distribution, and then also the fact that we're dealing with variances or standard deviations. Okay, so those are the things that you need for a chi-square test. So based off of the H1 or the HA, the alternative, this is a two-tailed test. So we're going to go ahead and draw the chi-square distribution. Remember, the chi-square distribution is skewed to the right. So something like that. Go ahead and redraw that real quick. All right, so now since we're doing a two-tailed test here, this means that we clearly have two criticals that we had to find, here and somewhere here. And we have two rejection regions. Okay, so what are the areas of these rejection regions? Well, remember that its alpha is 0.01, and because it's a two-tailed test, we have to divide alpha by 2, right? So we got to do alpha divided by 2. Every time you're dealing with a two-tailed test, you got to do alpha divided by 2. So this is going to be 0.0050. So that's what these areas are worth. Now remember, the chi-square distribution gives you the chi-square table gives you areas to the right. So we're going to look this up to give us the area to the right. If we want to look up the left side, we need to actually look up 1 minus that. So we need to look up 1 minus that number, which means we'll have to look up 0.995. Okay, so we'll have to look up 0.995, and we'll have to look up 0.005. So we're going to look up both of those values on the chi-squared. And the fact that we need to calculate our df. I forgot to do that over here. Since we're dealing with chi-squared, we need to do our degree of freedom. So 60 minus 1, n minus 1. So our degree of freedom is 59. So 59 degrees of freedom, and then those are my two values, 0.005, 0.995. All right, returning back to the chi-square table, we're looking at 0.995, 0.005 for my two tails. And we have 59 degrees of freedom. Now be very careful here. Here in this chart, you only have 50 and 60. Remember that, and we got 59 as my DF. So remember that the guideline is that you want to be conservative. So you don't want to give yourself more degrees of freedom. You want to give yourself less degrees of freedom to be conservative, okay? Because just to be on the safe side, basically. So to be on the safe side, you want to make sure that you restrict yourself rather than try to give yourself more freedom. Okay, so this time, because of that, we're not going to go to 60. We're not going to use 60 here. We're going to actually use 50. Okay, we want to go to the closest smaller value. All right, which in this case, 50 is the closest smaller value. Okay, the smaller value of the two. So we're going to use 50 degrees of freedom. That's key there. 50 degrees of freedom because it's not in our table. And then 0.995. So let's look up that value first. So that's going to be 27.991. So let's go ahead and write that down. And then our next one it's right over here, 79.490. Okay, 79.490. I'll write that down. Okay, so let's go ahead and label that on our chi-squared curve. All right, so we got our criticals. Now we can calculate our chi-square test. So I'll write down the formula again just so that you have it for your reference. So n minus 1, so we got 50 minus 1, or was it 60? It was, I believe it was 60 minus 1. Yeah, 60 minus 1 times s squared. S squared was 36. Sigma squared is 64 from the claim. Okay, we're going to calculate that. We get 33 point, and let's say we're rounded to 2 decimals, so 33.19. All right, so that's going to be somewhere between these two critical values, right? So probably closer to here than anything. All right, so that's my chi-squared value, somewhere around there, which means we are outside of our rejection regions. So we're not inside the red, so that means we're going to fail to reject here. So our decision is to fail to reject the null hypothesis, which means for our conclusion, we're going to say not enough evidence. In this case, our claim belonged to our null, so we're going to say there's not enough evidence at the, I believe it was at the 1% level of significance to reject the claim that ... All right, and that's problem number 9. All right, so we're in the 10th and final problem here. So it says a magazine claims that 75% of all teenage boys have their own radios. A researcher wished to test the claim and selected a random sample of 60 teenage boys. She found that 54 had their own radios. At a 1% significance level, should the claim be rejected? All right, so first off, we're dealing, just by looking at the problem, we're dealing with a percentage here. So that means we're dealing with a proportion. So it says that the claim was that the 75% of the teenage boys have their own radios. So that means that's P. P is, so it's saying that P is 75% or 0.75. And then, so that's our claim here, first off. So we have our claim is that P, the proportion or percentage, is 0.75. So that clearly belongs to our null hypothesis because that's a statement of equality. And then it doesn't say, it says a researcher wished to test it, but it doesn't say whether the researcher thinks it's greater than or less than. So we're going to say it's not equal to. All right, so now they took a random sample of 60 teenage boys, that's my N. And then she found that 54% had their own radios. Or 54 had their own radios, not 54%. So this right here is my X. This is saying how many people had their own radios. So that's how many boys. So 54 boys had their own radios. That's our success. Alpha is 1%. And then, okay, so that's basically all the information they give us. So that means, remember, to calculate our p hat is from our sample. Remember the formula for that is x divided by n. Okay, so to calculate our sample proportion, this is for the sample, we take the fact that there's 54 boys that had their own radios out of 60 and convert that to a decimal. So 54 divided by 60. So that's going to be 0.90. All right, so that's my p hat. So we know our p hat is 0.90. So let's write that here. P hat is 0.90, not 0.60. 60 boys, 54 had their own radio. Okay. Okay, so clearly, since we're dealing with proportions, percentages, that kind of stuff, we're going to be using some kind of z-test for a proportion, right? So we're going to be using a z-test for proportion. But first off, we got to see if we can actually do the test, because it's possible that we can't use the test at all. So what is the condition? Remember that the condition was that the n times p has to be greater than or equal to 5, and that's a simple, I'm just saying and, n times q is greater than or equal to 5. Okay, so both of those have to be true. So we're going to test to see if that's true. So let's do that off to this, let's do that over here. So we got n is 60, so we got 60 times p greater than or equal to 5, and then 60 times, what's q? Remember that q is 1 minus p. Okay, so in this example, it's q is equal to 1 minus p. So p is 0.75, so it's 1 minus 0.75. So if p is success, q is failure. So in this case, it's 25%. So that's going to be over here. Okay, so first off, we're going to see if that's true, just to see if we can do the test. I want to remind you that that's how you do it. So this is going to be 45. So that passes that test. And then for the next one, you're going to get 15, so that passes the test. So it passes both of them, which means that we can go ahead and use the z-test for a proportion. So for part A, z-test for a proportion. Okay, so we can go ahead and use the test. So going ahead, I'm going to go ahead and put this in a bubble. So going ahead and continuing, we see that based off of the H1, this is a two-tailed test. So since we're using a z-test, we're going to have to... Oh, and since we're doing a z-test, we're going to have to show you both the p-value and the critical value. So we're going to have to show you how to do that, both of those. So before I get to that, let me just do the critical values. So since we're doing the critical values, there's going to be two of them because it's a two-tailed test. We know that our alpha, I believe our alpha was written down. Let me see. No, I didn't write it down, the alpha. At the 1% significance level. So alpha is 0.01. Remember, every time you have a two-tailed test, you have to do alpha divided by 2. So you got to cut it in half. So in that case, it's 0.005. 0. So we're going to look this up, and then we're going to look that up on the z distribution table. Okay, so let's go to the z distribution table. So we're going to look up as close to 0.005 as possible. So looking at this chart, the closest thing to 0.005 are these two numbers, 0.0051 or 0.0049. So you could pick either one of those. I'm going to go ahead and choose 0.005 or 49 here. But again, it doesn't matter which ones you choose because they're both equally as far from 0.005. But I'm going to choose 0.0049. In that case, I get negative 2.58 as my z critical. Now, because it's a two-tailed test, that means I got the positive version as well. So let's go. So negative 2.58 and positive 2.58. Okay, and that's for a two-tailed test. So now we can clearly, so that's for the critical value method. So let's put this under critical value. So let's put this on the critical value method. And then we're going to do the p-value method as well in a little bit. So let's go ahead and calculate our test statistic. So we got to calculate our z-test. Remember that the formula for z-test is x bar minus, oh, I'm sorry, it's p hat minus p, divided by square root of pq over n. Okay, so that's the formula for the z-test. So our p hat, we said was 0.90. Our p is 0.75 over square root of p, which is 0.75. Q we calculated earlier, that's found by doing 1 minus p, which is 0.25, divided by n. There were 60 boys that were surveyed. And then we're going to go ahead and calculate that. I would highly suggest doing the numerator and denominator separately just to be on the safe side. If you're not comfortable with using the calculator, doing it all at once. So I get a z-test statistic of 2.68. Okay, so that's my z-test. So now we're going to So now we're going to show you the p-value versus the critical value. So this is the critical value method on the right-hand side. P-value is going to be down here. So for the p-value method, we go ahead and label our z-test there, which is 2.68 around here. Now, because it's a two-tailed test, we got to do the negative version over here as well. Then we're going to shade our p-value, which I will do in blue. P-value is blue, rejection region is red. So because we need so we're going to look up the area for negative 2.68 because that's easiest, okay? Because the z-chart gives us the area to the left. So we're going to look up this area, and then we could double it to get both areas, okay? So let's look up the area on the left blue. So negative 2.68. So in this case, if we look up negative 2.68, it's going to give you an area of 0.0037. So that's what this area is worth, 0.0037. Same thing for that area. That area is also worth the same. So basically, you're going to double that area to get the p-value. So you get 0.0074 for the p-value. And then you're going to compare your p-value to alpha. Is that true? If that statement is true, if it's less than or equal to alpha, you're going to reject. Remember that our alpha was 0.01. 0.0100. So is that true? Well, if you compare those two, you can clearly see that yes, it is actually less than alpha. So this is true. So that means that we reject our null hypothesis. All right, that's the p-value method. Now the critical value method, we find the critical values, which I showed you how to do already. These two. You're going to draw the curve. You're going to label your critical values on there. So negative 2.58, z critical there, and then z critical here. Shade your rejection regions. For me, it's red for rejection. All right, and then we're going to label our z-test, which we calculated over here, which was negative 2.68, which is somewhere around here. Okay, that's from right there. All right, clearly we are in our rejection region. We're just barely inside it, which means that we are going to reject the null hypothesis. All right, so whichever method you use, you're still going to get the same conclusion and same decision. So our conclusion here is that we're going to, so that means we said there is enough evidence. Sorry, I put not. It should be there is enough evidence. So there is enough evidence at the 1% level of significance to, and then looking at our claim belongs to our null, so we're going to use the word reject. To reject the claim that ... We'll go ahead and insert the claim. All right, guys, that's it for the Unit 8 review. So again, like I told you, I can introduce any of these types of problems, and you got to figure out what test to use and then actually perform the test depending on the question that I ask you, and also some conceptual stuff. But I hope you learned something from this video. I hope that you found this useful, and I'll see you in the next one.